Right, in this video we're going to look at finding critical regions and finding critical values. Just as a quick starter, here we go. I'd like you to see whether you can now define what is meant by 1. A test statistic, significance level, a one-tailed test, a two-tailed test, a null hypothesis and the population parameter. If you're not sure about those definitions, then please go back and check them in your textbook and make sure you get familiar with them. When we're carrying out a hypothesis test, you always assume the null hypothesis. So we always assume that the null hypothesis is true. And what we're actually doing is we're considering how likely the observed value of the test statistic, how likely is it to occur. If this likelihood is less than the significance level, then we reject the null hypothesis. So if we're testing at the 5% level and the probability of it happening is less than 5%, we reject the null hypothesis. If it's greater than 5%, then we accept the null hypothesis. On this slide, we've got a uniform distribution, a probability distribution, a uniform probability distribution for a die. And the probability of throwing a 1, 2, 3, 4, 5 or a 6 remains constant. It is 1/6. So we can do exactly the same sort of thing for a binomial distribution. So for example, if we were to plot the random variable x modelled on the binomial distribution for n items and the probability of success was 0.5. So if we worked out each of these probabilities, so probability x equals 1, probability x equals 2 for our n, and 0.5, if we put them in the calculator and worked out the probabilities, we would get this distribution here below. When the probability of success decreases, so here, in this question here, P is 0.2 and all our probabilities are down towards the skewed down in this end of the graph. Similar sort of shape, and if P was larger, so 0.8, they're up at this top end. So the higher probabilities appear on the right because the probability of success is high, and the higher probabilities appear on the left because the probability of success is low. It was 0.2. So here, Joe, we've got an example. We're going to look at critical regions. So Joe wants to see whether a coin is biased towards landing on heads. He tosses the coin 10 times and counts the number of times x it lands head uppermost. What values would lead Joe's hypothesis to being rejected? So if we're testing at the 5% level, to reject his hypothesis, we would want to look at these extreme values where it would be unlikely that the coin would be unbiased. So their combined probability is limited by the level of significance. So for example, 5%. So we're interested in how likely a given outcome is likely to have happened just by chance, assuming the null hypothesis is true. So if the null hypothesis is true, then these extreme probabilities, these extreme values have just happened by chance. So if you're going to use the calculator, using your ClassWiz calculator, there is a bit of trial and error involved. We're just going to try some values, going to input some values and see which one will give us the first result, which is less than 5%. So when we read the question, we know we've got a random variable x modelled on a binomial distribution. We tossed a coin 10 times, the probability of success is 0.5. So we're going to assume our null hypothesis would be that it is actually equal to 0.5, and our null hypothesis, so it's a fair dice, our null hypothesis is going to say, well, no, it is actually going to be greater. If it's biased towards heads, it's going to be greater than 0.5. So we just take some random values. We can actually, you have these tables in your formula book and also at the back of your exercise book. So if you look for the P, the values which give you a probability of 0.5 and n equals 10, you can actually read these values across. But these are the values where P is less than or equal to x. Right, so we can see here, you can sort of make some sort of guess looking at these values here of what our critical values could be. So I'm going to work out the probability that x is actually greater or equal to 7. So if I put that in, that's the same as 1 minus the probability that x is less than or equal to 6 when I use my calculator. And I'm going to work out that probability. So when I did this, I worked out the probability x was greater or equal to 7 and worked out what 1 minus probability was less than or equal to 6 on my calculator. So I put in my x value was 6, my n was 10 and my p was 0.5, and it gave me a probability of 0.01718. Now 0.0178 is greater than 0.5% level 0.5. So there's insufficient evidence to reject the null hypothesis. Okay, so there's insufficient level evidence to reject the null hypothesis. So this is not in our critical region. So I then went one up. I worked out the probability x was greater or equal to 8. 1 minus probability it was less than or equal to 7, and got 0.0547. And again, 0.0547 is greater than our significance testing level, the testing at the 5% level, 0.05. So again, insufficient evidence to reject the null hypothesis because it's greater than 0.05. So there isn't enough evidence to suggest it's biased. However, if the probability we would see 9 heads or in even more extreme values, so 9 or 10 heads, so that means I need to work out the probability that x is greater or equal to 9, which is 1 minus the probability x is less than or equal to 8. And when I do that, I get a probability of 0.0107. Now 0.0107 is less than 5%, which is a level of significance that we're testing at. So therefore, it is very unlikely. So this is very unlikely. So we reject the null hypothesis because it's less than 0.05. So we can conclude there is sufficient evidence. So we reject the null hypothesis and conclude that there is sufficient evidence to suggest that the coin is biased. So following on from this, because 9 is the first value to be less than 0.05, then we say that our critical region, remember there are 10 values altogether, so our critical region therefore is going to be where x is greater or equal to 9 or less than equal to 10. 10 because there are 10 things altogether, Rn equals 10. So this is the region where we reject the null hypothesis. And we call that our critical region. Okay. And obviously 0 to 8 is going to be our acceptance region, but generally speaking we're interested in the critical region because this is a region where we do not reject the null hypothesis. Any value on the boundary of the critical region is called a critical value. So in this first example here, the coin is thrown. X is the number of heads that we obtain in n throws. Determine the critical region for each situation where we are trying to establish if there's a specified bias. The level of significance is 5%. So anything that's less than 5% is where we reject the null hypothesis and we can determine a critical region. So we're looking to see, to establish if there's a bias. So we're looking at the number of heads we obtain in n throws. So a coin is thrown 5 times, so our n equals 5, and we're trying to establish if there's bias towards heads. So our null hypothesis would be that there should be a colon, p equals 0.5, and our alternative height is we're looking to see if p is greater than that. Is it biased towards heads? And we'll got binomial distribution where n equals 5 and p equals 0.5. So we want to just try different values to see which is the first one to give us a probability of less than 5%. So my first try is going to be that x is greater or equal to 4, which is 1 minus the probability it's less than or equal to 3. So this gives us a probability of 0.1875, which is greater than 0.05, greater than our 5% level. So there is insufficient evidence to reject the null hypothesis, or we accept the null hypothesis. So here I've now gone on and I've worked out the probability. I've gone one up. Probability x is greater or equal to 5 is 1 minus the probability it's less than or equal to 4. So, which gives us a probability of 0.03125, which is less than the level that we're testing at, the significance level of 0.05. Therefore, we can reject the null hypothesis. So, there is only one value. Therefore, our critical region, therefore, is x equals 5. Greater or equal to 5, and we just worked out less than or equal to 4. So, our critical value here is 5. In the second example, a coin is thrown 10 times and we're trying to establish if it's biased towards heads. So we've changed from 5 times to 10 times, otherwise it's basically the same. So we have a null hypothesis is that it's not biased, the probability is actually 0.5, and if it's biased towards heads, the probability of getting a head is going to be greater than 0.05, and we're still testing at the 5% level of significance. So again, we're going to take some values and see what happens. So we'll first of all look at the probability that x is greater or equal to 8, because it's biased towards heads, so we're going to get 8, 9 or 10 heads. So we know that's the same as 1 minus the probability that x is less than or equal to 7, and we'll work that out on the computer, on the calculator. It gives us a probability of 0.05469, which is greater than our level significance that we're testing at, so it's greater than 5%. So we accept the null hypothesis in this region. So we carry on and work out the next probability. So moving on to working out the probability x is greater or equal to 9. So 1 minus the probability it's less than or equal to 8, and putting all the data into our calculator, we get a probability of 0.0107, and this is less than our 5%, so less than 0.05. So we can therefore say that this value here, 9, so probability x is greater or equal to 9, so that's 9 and 10 fall into our critical region. So therefore, our critical region is where x is greater or equal to 9, but less than or equal to 10. And all this comes from the fact that our probability is less than the 5%, the level of significance that we're testing at. In this last example, remember in this test we've been looking to see whether looking at the number of heads we obtain out of n throws. But in this question it says a coin is thrown 10 times. We're going to see if it's biased towards tails. So if it's biased towards tails, that means the probability of it landing on a head is actually going to be less than 0.5. So our null hypothesis stays p equals 0.5, and our alternative hypothesis is that p is less than 0.5. Looking here, we've got our x is the number of heads that we obtain, and the coin is tossed. 10 throws, and p, probability of success, remains at 0.5. So we're going to, because we're looking biased towards tails, the number of heads we're looking at is going to be at the lower end. So I'm going to look at the probability that our x is less than or equal to 2. When I put this into the calculator, I get a probability of 0.054685 and 0.054685 is greater than 0.05, as we're testing at the 5% level of significance. So it doesn't fall in the critical region. We would still be accepting the null hypothesis. Go on and check. Go down, and we're going to now work out the probability that x is less than or equal to 1. So in this question we're throwing a coin 8 times, and we're now interested in how many heads would suggest it was a biased coin. So it could be biased towards tails, it could be biased towards heads. All we know is that it could be biased, and we're going to work out the critical values now with a 5% level of significance. So we've got our null hypothesis. Our null hypothesis would be that p is equal to 0.5, and our alternative hypothesis is that p is not equal to 0.5. Our coin is biased. So it could be biased either way. And because we're testing at the 5% level and we're doing a two-tailed test, that means we have to split our 5%. So we're doing a two-tailed test because all we know that it is not equal to 0.5. So we have to split the 5%. So we'll have 2.5% in each tail. So we're going to look at the region in the right tail. So the right tail over towards this end. So I'm going to check out the probability that x is greater or equal to 8. 1 minus the probability that x is less than or equal to 7. And this gives me a probability of 0.0039006 and 0.0039006 is less than 0.025. Now, because it's less than this, at this level we would reject the null hypothesis. Now, I ought to really go and check the probability that x is greater or equal to 7, which is 1 minus the probability that x is less than or equal to 6. And this gives us a probability of 0.03516 and 0.03516 is greater than 0.025, so we accept the null hypothesis. So we accept our null hypothesis for this value here. So therefore we have worked the first value where we reject the null hypothesis is where x is greater or equal to 8. So therefore our critical value is going to be x equal 8. It's the first value where the probability is less than the significance level, and that is the value that gives us our critical value, our critical region, or our critical value. We now need to look at the lower tail, the tail on the left hand side, and we're looking for the value for x, which gives us a probability which is below 0.025. So I'm going to work out the probability. Let's change the pen colour. Probability that x is less than or equal to 1, which is 0.035156625 and 0.035156625 is greater than 0.025. So I'm going to try the probability that x equals 0. So when I work this out, probability that x equals 0, you can see it on the table here, and you will get these values in your book as well, so you don't need to use a calculator. Just look in your formula book, CDF binomial table. You must look for the values where p equals 0.5 and n equals 8, or if you just prefer to use your calculator, menu 7, variable, binomial. Well, I'm going to use PD this time because it's just the probability it equals 0. So I'm going to put 0, n is 8, p equals 0.5, and my probability is 0.00390,625. And you can look at the symmetry of the graphs here, and you probably just be able to work that out anyway. So that will give us, we now know that 0.00390,625 is less than our significance level, 0.025. Testing at the 5% level, 2-tail test, 2.5% in each tail. So any value, so therefore x equals 0 is our other critical value. It's the first value that falls below 0.025. And there we have it, the top tips for critical regions here. So I'll let you read through those, and you need to just go and have a go at some of the questions in the rest of the chapter. I think I've got enough information there. I'm going to put some work solutions up on YouTube, and if you need any help, just get in touch. Okay, so I will put some work solutions from exercise 7B and C, mainly C, and the rest of the chapter.